Okay, so reminder, we were talking about triple integrals, and here's the sort of the big picture overlay of how you find bounds on a triple iterated integral. You're looking at your solid here, and once you've decided what order you're going to do your differentials, which integrals are inside of which integrals. Here we're taking the x integral on the outside, doing the x slicing first, you might say, and so you determine the range of values of x by looking at what these x slices look like. Keep in mind an x slice is a slice perpendicular to the x-axis. Okay, well, so the first x slice is back here, and that corresponds to our lower bound, etc. for the upper bound. Once you have found your x bounds, you fix a value of x, or whichever is your outside variable, and you confine the rest of your consideration to that x slice. This is going to seem weird, right? You're like, but what about this stuff over here? You'll get to that for a different value of x, right? Okay, so we are looking at this x slice, and on that x slice, we ask then what's the range of values of, let's say, y. Well, on that slice, that x slice, here's what a slice perpendicular to the y-axis looks like. I appeal to your geometric intuition. That's going to give us these little vertical line segments. And those vertical line segments, well, the first one is there, which gives us a y-coordinate. And the last slice is there, which gives us a y-coordinate. That gives you your y1 and your y2. Okay, finally, with x and y now fixed, and so reminder, x we're fixing, and then now we're also fixing a y, and between that x and that y, we're now confined to that slice of a slice, right, of our original solid. And to find the range of values of z, well, there's the lowest value of z. There's the lower z bound. There's the highest value of z. There's your upper z bound. Those are those numbers there. Okay, so let's get our hands dirty and actually do one in practice. By the way, note, you do have 6 different choices here of how to do your slices. With double integrals, of course, there's only 2 choices. Which one's first? Right? But with triple integrals, there's the 3 choices of which one's on the outside, and then, of course, you have remaining 2 choices for which one comes next. Right? So 3 times 2 is 6. So that's a lot of choices. That's both bad news and good news. It's good news because you have flexibility. It's bad news because you have a lot of decisions to make. Right, a lot of different choices to analyze. So we're going to talk about the how to make that choice as we go through this. But ultimately, it's you just got to kind of look at it and do whichever one's going to make your life the easiest. Okay, starting with this example, we have this domain bounded by those 4 planes. Now, there is a geometry problem that starts with most of these kinds of questions, or many of these kinds of questions, where the domain is described algebraically, but you need a picture. And you've got to have a picture. The picture is what's going to tell you which points correspond to certain bounds. And those points, it is from the picture that you'll be able to determine what surfaces are they on, and therefore which equations should I be looking at. It all comes from the picture. Okay, so I cannot emphasize enough when you're doing one of these problems, make sure that you have a good picture. Step 1, look at the algebra you're given, draw the picture. Okay, so here we go. X equals 0. Fine. Sorry, that was y equals 0. X equals 0. There we go. It's that plane. Right. Next, y equals 0. That's this one. Got ahead of myself. Z equals 0. That's this plane. Oh gosh, and then this last one, x plus y plus z equals 1. Gosh, how do we draw that thing? It's going to be kind of angled, kind of back, sort of leaning back, if you will, away from us, you might say, from the z-axis. And now, the picture that I've drawn here, highlighted in colors, is really, really hard to work with. It's hard to see what's going on there, right? So, when you draw these pictures, is entirely possible that the first thing you draw will not be the picture that you should be working from. You might need to look at that and think, okay, well, what did I learn from what I just drew here? And having learned what I have learned, how can I then draw a better picture? Right? So don't expect to just first draft make a beautiful picture. Be willing to sort of do this in stages, yeah.
Why is that? Why is the angle?
Oh, well, because we know the normal vector is 1, 1, 1, which is like that, if you will. And so perpendicular to that, it's got to kind of, this is pointing kind of up-ish, and that makes it kind of lean back. Yeah. Right. Okay, so having drawn this, look, I can see the first 4 planes that I drew were those are the coordinate planes, and this 4th plane here just kind of cuts through, kind of cuts off the corner, if you will, of the first octant, and thus makes this solid. Okay. Don't forget this word bounded, right? There are quite a few different regions that R3 is chopped up into by these planes. We're not interested in all of them. We're interested in the one that is bounded by those planes. And this is the only region that is in fact bounded. Okay. All right. So now that we have a picture, let's talk about how to slice. By the way, again, 6 different ways to go. Arbitrarily, I'm going to do this one. In this case, it kind of doesn't matter. You can see there's a lot of symmetries in this picture, and it's not clear how any one variable is playing a role that's particularly different from any of the other variables. So here we really do have a lot of flexibility. I picked this one again arbitrarily. Let's just go with it. So we're doing our X slicing first. X slices of this solid. There's our X-axis. X slices are like this. And again, I appeal to your geometric intuition as to what do these slices look like. What happens when you take a tetrahedron like this and slice it by a vertical plane perpendicular to the x-axis? You just have to look at the picture and think about it, right? And I assert that it's a triangle like this. Okay. Now, to find the z bounds, we've got to find the first one and the last one. I said z. I'm sorry. The x bounds. We're working on our x slices. So our first x slice is back here. And what can I say about that slice? Well, that entire slice is sitting inside of the plane x equals 0. So that entire slice being in that plane clearly telling us what x is, that's our x bound. That's our lower x bound. Is 0. Okay, everybody on board with that? So now next question, where's our last slice? Our last x slice? Well, as we make these slices, as we go further along the x-axis, our last one is going to be there at that point. And now I want to talk about how you figure out what that value of x is. So what is the corresponding x bound corresponding to that last x slice? It's actually very similar to how we did this with double integrals. Bounds correspond to points. Points sit on certain geometric objects. In the plane, it was curves. Now it's surfaces. Okay? I'm just going to say geometric objects. And those geometric objects have equations. Once you identify the appropriate equations, then you solve for what you want. It's just like with double integrals, except now the pictures are three-dimensional and there's 3 variables. But it's strategically the same. So, okay, what can we say about that point there? Here, let me switch color. Well, yeah, no, I'll keep it green. That's fine. Okay, so what can I say about that point? Well, it's on this plane, I notice. It is also on this plane, I can see from the picture. And it is on this plane, I can see from the picture. Right? So in fact, this green point that I'm interested in here, the point that defines my upper bound for my x integral it's defined by those 3 planes. Right? So, but we're almost done. We're at least halfway there. The bound is determined by that point. I see the point. The point is on certain geometric objects, namely surfaces. I've identified those surfaces. Now I've just got to write down the corresponding algebra. So this one is y equals 0. this one is z equals 0, and this one is that. Okay, so bounds relate to points. Points are on surfaces. Surfaces have equations. I know the equations. And the very last step is solve for what you want. Right? We are looking for, I remind you, an x bound. Solve for x in that algebra, right? Take all of this algebra together, solve for x. This happens to be easy because, well, if y and z are 0, that just says x equals 1, and that is our upper bound, and that's what goes there. Everybody see the process? Okay. All right. I'm not going to do this whole thing because we've got a bunch of examples to do, and the process is analogous. I'm going to go to the parts that I think are the most interesting, right? So let's go to the y integral here, the second integral. And I want to look at the upper bound. Where does that upper bound formula come from? Okay, well, that upper bound, now keep in mind, we're looking at the second integral. That means that x is fixed. We're confining our attention to this x slice. On that x slice, I'm looking at y slices perpendicular to the y-axis. Right, so what do those y slices of the x slices look like? Well, they're line segments, kind of like that. Okay. The last, we're looking for the upper bound here. The last one of those slices happens at that point. So let's ask now, at that point, what do I know? What can I say about that point that tells me about that upper bound? And again, bounds correspond to points. We've identified the point. Next question, that point is on what surfaces? After we identify the surfaces, we then have to write down the equations and then do a little algebra. Okay. All right, well, that point, I noticed two surfaces right off the bat. That point is on that surface that has that equation. It is also on that surface that has that equation. And this is unsatisfying. I mean, we look at that and we think, well, yes, the point I'm looking for is on those two planes, but so are all of those points. How does this identify the point that I'm interested in? I'm interested exclusively in this point. So what is it about that point? What more do I know about that point that will allow me to write down a formula for it? And the answer is an easy one to forget. The answer is, don't forget, we are confining our attention to our previously designated x slice. So x is previously chosen. So x is fixed. Right? We're on the yellow plane and the orange plane, and we know x. So in fact, when we solve here, solving for y, our y ends up being a function of x, and that's okay because x is fixed. And we've chosen an x, and this y depends on that x. Okay. Just like with double integrals. Okay. All right. Okay. Lastly, what about the upper z bound? The upper z bound. Well, for the upper z bound, x is fixed. Y is fixed, and so we are now looking on a y slice of the x slice. We're looking at this line segment, is what that slice of a slice looks like. And on that slice of a slice, well, by the way, clearly z starts at 0. That's an easy one. Right, what is the upper bound? The upper bound is going to be determined by that point. That point is on this plane. Again, thank you, picture. The picture is what tells us which algebra to look at. Okay. Oh, by the way, don't forget that x is fixed, and so I can leave my answer in terms of x. Y is now also fixed, so I can leave my answer in terms of y. And here it is, my z bound that I'm interested in. I guess I'm using red. That z bound, solve for z in here, and I get this. 1 minus x minus y. Everybody happy? Okay. All right. All we're going to do for most of the rest of this class, and possibly all, depending on how slow I go, is more examples of this kind of thing. And I've picked some examples that I think that illustrate different kinds of curveballs that you might have to try to hit, right? Different levels of challenge, kinds of challenge. But they are, in fact, just a bunch of examples. So here we go. The next one. This is a geometric challenge. Ours are region in the first octant between that paraboloid and that plane. You got to draw the picture. This paraboloid, of course, something like that. By the way, it's a little hard to draw a fourth of a paraboloid, right? That's sometimes take a little practice. So I would encourage you to take a few moments, right, and to put pencil to paper. Try to do it on your own at first, right? And you're not going to do well. Right? And that's okay. And then look at your picture and ask what you don't like about your picture. And the more you criticize your picture, then you have more opportunities to correct it and improve it. And of course, obviously, I encourage you to make reference to pictures that I've drawn, right? And ask you, so what is it about this one that looks kind of sort of okay, and maybe mine doesn't, right? What's the difference? What specifically? Right? Look for details. Let me remind you also that if you are really struggling with drawing, which is unavoidably important in this class, right? If you are struggling with that, come to my office hours, right? And we'll talk. I can give you a short discussion of some quick pointers that'll kind of get you on the right track of being able to do that better. Okay. All right. So there's that paraboloid. Then there's this plane. That didn't go well. There we go. And in the first octant, between those two surfaces, well, you can see what this. We've got this weird little shape, and that's our domain. Okay. And we can start slicing it up. By the way, no particular reason. I'll say I'm going to do my Y slicing first. I'll come back and comment on that later. Part of my motivation here is just to show you don't have to always do X first. Okay. But I have another motivation, and I'll tell you that later. So, doing a Y slice, what happens when you take this solid and slice perpendicular to the Y-axis, and well, you're going to get something that looks kind of like that. And you can think about the first slice and the last slice, and play the usual game. Let's from this point of view, by the way, here's the first slice. Lucky break. That one's clearly got Y equals 0. That's nice. Sometimes you get lucky. And as you slice along, here's your last slice is that point. Right, so to get our upper Y bound as we're slicing in the Y direction, I need to understand that point. And what do I understand about that point? Well, I know several things about that point. One is clearly that point is on that plane. You can see it right there. Right, it is also on that paraboloid. And I know something else about that blue point. Again, you got to have the picture. The picture is what's going to figure this out for you. There's a lot of points that are on both that plane and that paraboloid. There's loads of them. Look at all of them. There's all these different points here. What distinguishes the one we are interested in? As it turns out, as I see from the picture, it's on that plane. X equals 0. Right, so I'd already identified this plane y equals z equals 1, and this surface z equals x squared plus y squared. The picture is what tells me because the nature of this shape, just as it turns out, I need the point that's on the sort of the back face there, where x equals 0. Everybody on board? Again, solve for what you're interested in. We're doing y slices, don't forget, right? Doing our y slices. Therefore, in this, I want to solve for y. And there you go. How are we doing? Is everybody on board? Everybody see how important the picture is? Okay, please don't try to do this without a picture. For two reasons. First of all, it'll make your lives much, much harder to not have a reasonable picture. By the way, your picture doesn't have to be beautiful. It doesn't have to be, frameable. Right? But it has to be reasonably representative of, qualitatively at least, what does your thing look like? Right? So, anyway, it's very important to have a good picture. Makes your life easier. Second reason, though, don't forget when you write down your answer to a question of this sort, the goal is not simply to get the right answer at the bottom of the page. You're communicating a thought process. Your decision-making of how to slice, which points determine bounds, which algebra you therefore subsequently do to get those bounds. That's a thought process, and that thought process comes from the picture. Right? So you have to give me a good picture so that I can have some chance of possibly understanding your thought process, and your thought process is what you're graded on. Right? So keep that in mind. This is not a optional, if you might find it convenient. This is definitely a mandatory thing. Okay. All right. Okay. Now here's a different point of view you can take on this. By the way, so we just concluded that our bounds were from 0 to 1. We found that that upper bound there, y equals 1. Let me show you a different way that you can approach this question. And I think this is a really nice point of view. Some situations, this being one of them, your life becomes a lot easier with the following point of view, and that is to make the observation that the ranges of values of x and y on R there's R, right? Look at the different values of x and y on that region. I claim exactly the same as on the shadow of R down here. In other words, if you just take all these points and push them straight down, like that, in that process of making a shadow or projecting down to the xy plane, notice that in that process z is the only thing that changes. X and y don't change. So this is a powerful observation. I mean, what I'm interested in finding these bounds here, these bounds for the x and y integrals, all they are is what's the range of values of x and y. And this observation here says the range of values of x and y on the yellow solid is the same as the range of values of x and y on the green shadow. So we can just as well say fully on that solid. That was hard to draw. My picture didn't work out that well anyway. Just look at the shadow. Big, nice, convenient, yeah.
Is that why you chose y?
Yeah, so that's why I chose x and y. I'll say it. I chose x and y to be my two outside most, because I look up at this thing and I see, look, this has got an easily understood shadow. Now I guess I should admit I could make the same argument going this way, right, and then look at the shadow over here. I guess really the best reason that I can give for why I chose to do these on the outside is about independent variables. And I look at this equation here and I think, do I want to solve for z in terms of x and y? Absolutely. I love not doing work, right? Or do I want to solve for x in terms of y and z, in which case I'm going to have square roots involved, and maybe it'll work out, right? But all else being equal, I just kind of shy away from square roots if I can possibly avoid them. Yeah. Okay. So let's take this point of view to figure out our next bound. Then, what is this upper bound? Let's say for x. So we're going to fix y. Keep in mind, right? Y. We found our y bound, so y is now fixed. So fixing a value of y. If I were looking at the solid, I would have to do business up here on that picture a hard-to-draw slice of a hard-to-draw solid. But I'm not going to. I'm going to say, well, I'm just going to do business over here. And that's what a Y slice of my shadow looks like. And on that shadow, things are a lot easier. By the way, let's try to understand the shadow a little bit better. That shadow is bounded by this curve. That curve, I can see from my picture, is the shadow of that curve. Where does that curve come from? Well, it comes from this plane and this paraboloid. So if the purple points that I'm interested in, if they're on both of those surfaces, then they satisfy both of these equations, and therefore x squared plus y squared is equal to 1. So that's the equation of my curve that I'm interested in there. Does everybody see what happened there? Again, you have to have the picture. I mean, to know, what does the shadow look like, you have to be able to see which sort of edge of your solid is the one that's projecting down to it. Yeah?
I feel like just based on the picture, it should be bound by the little curve underneath the Y slice there, you know?
Curve under. Oh, you're talking about this curve here? Yeah, well, that's sitting underneath. That is directly, well, let's say it this way, this is sitting directly over that. See what I'm saying? So if I want to talk about, what is the sort of what's bounding my shadow, what I've got in green there is on the inside of the shadow. Right? We're not looking at Z bounds yet. Right? So the bounds on the shadow are that purple curve. Yeah. Okay. So looking at the shadow, we have this equation, and let's see here. Y was fixed. My upper bound for x, as I move perpendicular to the x-axis, x starts at 0. By the way, that's an easy one. You get lucky sometimes. My upper bound, my last x point is that one. That point. That point is on that curve. That curve has this equation. Solve for x. Don't forget we've already solved for y. So x, the x that I'm interested in, is there. Yeah. Okay. Okay. So let's see. Yeah. So here's another point of view you can take. By the way, you can do this kind of all at once and say, look, this is what my shadow looks like. That shadow is a quarter disk, and this, kind of becomes a double integral problem. And quarter disk, we've done quarter disks before, and you don't even have to draw your pictures in that three-dimensional. So you can just draw the XY plane separately and say, look, there's my x-axis and y-axis, and here's a quarter disk, and just it's a double integral problem, and you get these exact same bounds. All right. Last question, then, what are the range of values of z? So with x and y fixed, given a value of given values of x and y, that point is going to determine my lower z bound. What do I know about that point? Again, play the game. That point is on this surface. That surface has this equation. This equation. Solve for what I'm interested in. I'm interested in z. Solve for z. And I get that. So my lower z bound is x squared plus y squared. Everybody see the process? Okay. Different domain. This one's the unit ball. There's another interesting twist that happens with this one. By the way, a sphere is a surprisingly hard thing to draw. Right? I mean, it's round, right? It seems like you could just get a Coke can and just kind of just trace around it, right? There's your round thing. But making it look three-dimensional, a little bit challenging, right? So think about, what I like to do is always kind of put a belt around it. to show the dimensionality. That belt is, visible from where, this part of the belt is visible from our point of perspective. This part of the belt back here is hidden. It's behind the surface. And yet I need to indicate where it is. And so my little cheat for making it look like it's kind of there, but I can't really see it, is to draw a little dotted line, like it's obscured, like it's a cloudy, something that I'm looking at. It's a pretty common choice. So anyway, there's our sphere. And let's think about our bounds. By the way, no particular reason. Let's slice in this order. dy, dz, dx. Highly symmetric. It doesn't really matter. Whatever. Okay, range of values of x. X starts there and ends there. What do I know about those points? Okay, I know several things. For one thing, those points are clearly on the sphere. Right? I mean, the sphere is the boundary of the ball, so yeah, I'm going to say, of course, there. What else do I know about those points? So here's the thing. There was only one surface that was really given in this question. I'm looking at the ball, namely what's inside the unit sphere. Sphere is the only thing given. What other equations could I possibly have to look at? Well, this is another one where you have to look at the picture and ask yourself what you know about the picture, what do you know about the surface, and what does that help you write down? In this case, I'm going to invoke the symmetries of the sphere. This point back here, this back point that represents my lower bound, that point kind of in the middle, right? Because spheres are highly symmetric. So it's on this axis. More to the point, it's in that plane, y equals 0, and it's also in this plane, z equals 0. You got to get that from the picture. Now, now that I know what I know about these points, again, solve for x, and in here, x, negative 1 and 1 are the two values that I get here. Now, by the way, which one is which? How do you know? Again, the picture, you have to kind of tell from the picture, but the lower bound for x is clearly going to be the one where x is negative. One of my algebraic options, negative 1 and 1. Only one of those is negative, therefore it's that one. Okay. All right. Now we fix the value of x. Moving on to, with those x bounds fixed, moving on to our z slices. What does it look like when I take my x slice? By the way, again, appeal to your geometric intuition. If you take a solid ball and slice it vertically, that cross section is a disc. What happens when I take z slices of that? Okay, well, a z slice is going to be a horizontal slice. If I have a vertically oriented disc and I take a horizontal slice of it, my z slices are going to look like this, I suggest. Okay. All right. So, for example, like that one. So where's the first one? Where's the last one? Well, okay, here's the first one. Here's the last one. What do I know about those points? And I know several things. As usual, these points are on the sphere. So I know that algebra. What else do I know about those 2 points? Geometric appeal, again. Spheres are highly symmetric. Thankfully. Right? I don't know what it would do if we didn't have these symmetries. We'd have a much, much, much harder problem. But spheres are highly symmetric. And if you take a slice perpendicular to the x-axis of this sphere, the lowest and highest points on that slice, I claim we're going to have y equal to 0. They're in the middle, if you will. Again, appeal from the picture. Yep.
How did you know which is the first Z slice and which is the last one? Like, why you said?
This is what our slices look like. Our slices look like this, right? And what we're interested in is the lowest value of z and the highest value of z. So least and greatest values of z being an upward pointing coordinate, mean lowest and highest. Okay. Geometrically lowest and geometrically highest. Yeah. Right. Okay. So, so these points, these z bounds, I know they're on the sphere. I know y is 0 by sort of symmetry of the sphere. Don't forget, I already know what x is. X has been fixed, chosen, because x is further to the outside in the integral, and solve for what you want. Here we're looking for z bounds, so I've got to look at this z right here. There you go. Everybody on board? Okay, let's see here. Lastly, what are the y bounds? With x chosen, with z now chosen and fixed, that cross section, my z slice of my x slice, is going to be, as usual, it's always a little line segment, right? That's the third sort of thing that I have to look at. I'm now interested in finding y bounds with x and z chosen. Well, my y bound, there's sort of the first point. It corresponds to my first y bound. There's my last point that corresponds to that upper y bound. Those points are on the sphere. X and z are fixed. Do the appropriate algebra, and you get that. Okay. So I hope you're noticing, I keep saying it, but I hope you're noticing yourself as well, how extremely useful it is to have a picture. Let me make another observation about this picture, by the way. This is a pretty good-sized picture. It goes most of the way across the page, and yet, despite going most of the way across the page, notice it's still arguably a little cramped, and in this part of the picture in there, there's a sort of a lot going on, and it wouldn't hurt if this picture had been a little bigger. What I'm hoping to persuade y'all of is that it's a huge mistake to make a little picture that's about that big. This is what a lot of students do. And then, you can just imagine what happens when you slices and bounds and labeling this and labeling that. And oh my gosh, you just get a mess. Uninterpretable mess. Again, bad because you need to be able to interpret your own pictures. And furthermore, the grader, that's me, needs to be able to interpret what you were thinking, right? And if the picture's too small, I can't make any sense out of it, then I can't give you credit for thoughts that I can't interpret. Yeah. Okay. Make a nice big picture. Okay. Moving along. This is one of my favorite examples here. It looks really easy at a glance, and then about 5 seconds later it looks intractable, and then about a minute after that you start to realize that it's doable. So why does it look trivially easy? Well, look, nothing's squared. It's just planes. Just planes. Easiest thing in the world. Right? And then you start drawing these planes, and you start to realize how oh my gosh, let's see, z equals 0, z equals x, x plus z equals 2, y equals 0, and y plus z equals 3. Right, so this is the first thing you write down, is all that purple stuff. And you think, get out of town. There's no way, right, that I'm going to be able to make sense out of that. Right? Okay, so again, at a glance, it looks trivial. 5 seconds later, it looks intractable. And let me show you how to break this down. And these can be really, really hard problems if there's nothing sort of particularly nice about these equations, but there is something really, really nice about these equations. And in particular, here's what it is. These first 3 equations have a wonderful common feature, and that is that they don't have any y's in them. Not a 1. Look at that. The first 3 equations, no y's. Now, chapter 12 reference. If an equation doesn't have a y in it, choose to think of it in either of the following ways. Either think about which direction that means the normal vector points, or think about how, well, if y is not in the equation, then the y coordinate plays no role in deciding if a point satisfies the equation, and therefore the y coordinate doesn't matter. Anyway, punchline, in all of these cases, all of these planes are parallel to the y-axis. And knowing that they're parallel to the y-axis gives you a way to simplify your process. I'm just going to start off by understanding these planes as, how they sit inside of the plane y equals 0, because y doesn't matter as far as, whether points satisfy these equations. So I'm just going to draw it inside of the plane y equals 0, and then I know y doesn't matter. I know these planes are parallel to the y-axis, then I'm just going to drag whatever I come up with parallel to the y-axis, and I know that that's all good. Yes?
How come you can just avoid, the equation y plus c?
Oh, we'll get to it. Yeah, no. We're not. I'm just. I'm not avoiding it. I'm procrastinating it. Yeah, totally. Okay, so inside of this plane, well, again, things might start off looking kind of bad in the sense that you have these 3 different lines and they don't all intersect. But you draw that picture and then you quickly realize that, okay, well, we're just talking about this. Which means I don't need about half of what I just drew there. I don't need all that stuff that was hanging off the edges. All I need is that. And if I drag that parallel to the y-axis, right, then I'm going to get a prism like this. Now, I'm not going to draw the whole thing. I mean, obviously it goes off to infinity that way and that way and that way. Right? But I've got a pretty good start on what this thing. This is we're starting with a prism, and on that prism we are then going to draw a couple of extra planes and think about how those. Don't think about how all 5 planes fit together with each other. Think about what those 2 new planes do to the prism. And not that bad, as it turns out. Y equals 0 is real easy. That's this thing here. So we sort of cut through, big vertical straight cut right through that prism with that plane. Lastly, this plane, y plus z equals 3. Maybe this one's a little bit hard, but not hard to persuade yourself. Oh, hey, no x's. If there's no x's, I know this plane is parallel to the x-axis. I'm going to draw over here in the yz plane, then drag parallel to the x-axis, right? And now I have to think geometrically here, but what's going on here is I've got this prism, and I've got a plane that's kind of cutting through it like this. Sort of an angled slice through that prism. So that gives you something like this. And now the problem's a lot easier to sort of get your hands on. We got a prism that's chopped on the left by that red plane and on the right by that blue plane, and so that's going to give you a sort of a piece of a prism, and putting all this together and redrawing your picture, not hard to come up with this as your picture. Everybody on board? Everybody see how there's a process there? By the way, and again I emphasize, you're going to have to draw a series of pictures. I here have the advantage of stylus, and I can erase and use colors and everything, so that's a big advantage. When you're doing this with a pencil, or a black pen, by the way, on the exams, right? Black pen. You're going to draw one picture, you're going to learn something from it, realize then how your picture is bad, and then you're going to draw a slightly better picture next. And then from that, you'll learn it, hopefully a little bit more, and then, after 3-4 tries, maybe come up with a good picture. All Okay, this done, picture done. How do we find our bounds? By the way, you got to be real careful about your order of your differentials. On this one, I'm gonna show you some bad choices. Oh, you had a question? Oh, okay, yeah. I'm gonna show you some bad choices just to show you what makes them bad, and then we'll eventually do it the good way. What if I did my X slicing first? Here's what X slices look like. And you can see this coming, but I'm going to hit that corner. In fact, I'm going to hit this entire big corner, namely edge. Right? And if you slice through that corner, then we know bad things happen when you slice through corners. In this case, what's going to happen is my upper bounds for Z that had been on this plane for low values of X are then subsequently going to be on this plane for high values of X. Right, so your upper Z bound is going to be determined by two different formulas. So you're going to have one integral for small values of X and then a separate integral for large values of X. I don't want to do two integrals. Right? So X slicing on the outside means you slice through corners, means I don't like it. Okay. All right. Right, so what about Y slicing? Let's do our Y slicing first. Okay, so here's our Y slices, and they look kind of like this. And you can see it coming. We're going to slice through that corner, and something really terrible, some sort of catastrophe will happen once I slice through that point. For one thing, the Y slices look like this on the left side, if you will, of that corner, and then they look totally different on the right side of that corner. So again, you're going to have two separate integrals on each side of which your answers are going to be qualitatively different. So let's not do that either. Notice though, very conveniently, doing your Z slicing first, your Z slices all look kind of the same. They all look like this. You don't slice through any corners, except at the start and end, of course, which is fine. And so that's our first choice. Okay. Once you've fixed a value of Z, right? In this case, as it turns out, we've got a rectangle, and so which of these we do first kind of doesn't matter. You can do your X and then Y, or your Y and then X, and sort of suit yourself. But let me point out that would not be so if I had changed this question a little bit. If this question had instead been X plus Y plus Z equals 3, then this would no longer be what that end side looks like. Then it would be something more like this. Our solid, just to make it clear what we're talking about here then, our solid would be like that. And then your Z slices would look like that, not a rectangle. And there you have to make a right decision, right? So looking at this green, slice of a slice, if I were to slice first perpendicular to the y-axis, I would hit this corner. So if the problem were different, like I have in purple there, then you definitely not want to do Y slicing in the second position. You definitely want to do X slicing in that second position. Okay. All right. So the picture is essential. Okay, let's see here. I have 30 seconds left. Gosh. Okay, one last example. Maybe I'm going to let y'all read this example. Let me just point to what the big trick on this example is. The big trick on this example is look at the projection. Our solid here is really hard to get a picture of. It's what's sort of stuck in between two separate paraboloids, and it's really ugly to look at until you project over here to the XZ plane where it's just a circle, right? This paraboloid and this paraboloid, where they intersect, the equation's easy to deduce, and so your x and your x and z bounds then are based on just looking at that circle in the xz plane, and then all it remains is to find the y bounds. So I'm going to let you all read this example, and we're going to start next time with physics applications. Okay, see y'all later. Have a good day.